All right. So as I was mentioning that this is topology of real numbers. Now, generally, topology is applicable for things beyond real numbers also. So it is going to be true for complex numbers and everything. So the idea is there's a math of real numbers which is applicable only on real numbers. Then there's math for other things. Topology is that math which is general, which can be applied to any different field that you're working on. So if you're working on something other than real numbers, even in that case, topology is useful. But luckily for us as economists, we never go beyond real numbers. Okay, so for us, complex numbers and all those things don't exist. So first we are going to define open sets, and then we are going to define some concepts using this concept of open sets. So set G, which is a subset of real line, is open if for every element in G there exists a radius delta, a positive radius delta, such that the set x minus delta to x plus delta belongs in G. Okay, so this is a powerful definition, which we are going to look at what it means. So why don't one of you give me an open set? Okay, so I see Anuradha. Anuradha, give me any open set on real number line.
Sir, 2 to 4.
2 to 4, very good. Okay, open 2 to 4. Thank you, Anuradha. So now I have this open set on 2 to 4, which I want to check if this definition holds for this thing. So the definition says that you take any element in this open 2 to 4, you can construct an interval around it. So let's say I take this point, which is, let's say, 2.1. So I can construct an interval around this 2.1 such that this interval completely lies inside my open set, the one that I had constructed. Very bad color to highlight. Okay. So this interval completely lies inside this open set. Now you can go as close to 2 as possible. Okay, so you may think of a number, let's say 2.001. But I can construct an interval around this also. You can take delta equals to 0.0001. So then the interval becomes 2.001 minus 0.0001, comma 2.0011. Okay, I don't know what this is going to be, whatever it's going to be. So even for a number very close to 2, you can construct an interval which lies completely inside this shaded region. But this definition will not hold for a closed set. So Himandi, why don't you give me a closed set, any closed set on real line? I can't hear you, Himandi.
Hello.
Yeah, now I can hear you. Why don't you give me a closed set? Any closed set?
Closed set is like you can take the same example with the closed intervals, right?
Okay. Yeah, sure. Let's do that. Okay, so now I'm taking the closed 2 to 4 set. Now, this condition is now going to be violated for some points. Okay, so this condition says that for every element in X, if you construct a neighborhood around it, that neighborhood should be contained in the set. But now if I construct a neighborhood around the number 2, right? If I take the number 2 and if I take 2 and try to construct any neighborhood around 2, the left part of this neighborhood is going to protrude outside the set. All right, so you cannot construct a neighborhood around it, which is going to completely lie inside the set. This is what we call a neighborhood, by the way, neighborhood. Okay, so that's why this closed 2 to 4 is not going to be an open set. Okay, so we know, okay, this is something which is coming from a parallel line of thought that we have, that okay, Yale bracket laga diya, so it's a closed set. So I know to begin with. Right now I'm trying to understand the definition and how they work. Okay, so we are not learning something new, we are trying to understand these definitions. Okay, so then we have this interval I 0 to 1 that is open. So that's an example. Okay. Any open interval 0 to 1 is an open set. This is an open set. This is an open set. Okay. This example, let's look at this example. The half open interval 0 to 1 isn't open. Okay. So open 0 to 1, open 0 to closed 1. So in this case, for all the points except 1, the condition is going to be satisfied. If you take 1 and construct an interval around it, the right side is going to protrude outside the set. No matter how small you make this, okay, you can push this as close to 1 as possible, but you cannot make it 1. You cannot make this delta 0. This thing is delta, right? This distance is delta, and this delta is required to be positive. That is the definition. Okay, this delta has to be positive. So you cannot make it completely 0. So this is half open set. You call it half open interval that is not open. Now the next proposition is an arbitrary union of open sets is open. Let's understand the word arbitrary here. The word arbitrary in mathematical language means either finite or infinite. Okay, so in this context, you could have, let's say, a union of sets ai going from I equals to 1 से लेके n, or you could basically have an infinite intersection here. In either of the cases, the definition holds. The definition says that an arbitrary union of open sets is an open set, and a finite intersection of open sets is open. So a union of AIs where AIs are open sets is going to be open for I equals to 1 से लेके n या infinity. But intersection I equals to 1 से लेके n is going to be open. All right. And infinite intersection, we'll talk about it in a bit. What happens to the infinite intersection? Okay. So as long as it's union, it could be finite or infinite. It's going to be open. But when it is about intersection, I know for sure that finite intersection is going to be open. Infinite intersection, we'll talk about it in a bit. But let's look at the proof of this thing. The proof of this thing is very nice. Okay. So suppose AI is a set of arbitrary collection of open sets. Okay, so AI is a set of sets. So you can say, let's say set A1 is open 0 to 1, set A2 is open 1 to 2, and AN, so on. AN is the set n minus 1 to n, and so on. You can construct it finite number of sets, or you can go on like this till infinity. So that's going to be a collection of sets. Okay, so that we have a collection of sets AI. It could be anything. I don't know for now. Now, if any element X belongs to union of AI, okay, so what am I checking right now? I'm checking if union of AI is open. That is what I'm trying to check. Okay, so I'm checking if union AI is open or not. So how do I proceed with the proof? So I take any arbitrary element in union of AI. Now, since this random element X, it belongs to union of AI, it belongs to some of the components of these sets. So either it should come from A1, or it should come from A2, or it should come from some random AN. At least one of the sets is going to contain it. Okay, so if X belongs to union of AI, it means that X belongs to some AI. Okay, I'm not saying that it's going to lie in every AI, but at least some AI is going to be containing my X. That's how it ends up in union AI. Now, since AI is open, there is delta positive such that X minus delta to X plus delta belongs to AI. Okay, so So what I'm saying is that X belongs to union of AI, which implies that X belongs to some AJ set, which means that there exists delta positive since this AJ is also open. Okay, so there exists a delta positive such that X minus delta to X plus delta is a subset of AJ, right? Because AJ is open and X is an element in AJ. Okay, now since this X minus delta to X plus delta is a subset of AJ, what this implies is that X minus delta to X plus delta should be a subset of union of all AIs. Okay, because if it is a subset of one of the set, it must be a subset of the collection of all the sets as well. So I started with X in union AI, and I showed an interval which is around X in union of AI. So these two things basically prove that union of AI is open. And here I have not used the fact about union being finite or infinite. So this proof is general. It holds for all kinds of unions, finite or infinite. Okay. Now let's look at intersections. So for intersections, what I'm saying is that I'm going to look at only finite collection of sets. Okay. So this is part one. Let's look at part two. So let X belong to intersection of AI for I equals to 1 select sum n. What this means is that X belongs to AI for all I. For every element for in this collection of sets, X should be in this collection of sets. There should be no element of this collection which does not contain X. Okay. So this implies that there exists delta I such that there exists some delta I positive such that X minus delta I to X plus delta I should be a subset of AI. And this should be true for all I. This should be true for all I. For every element, I should be able to find a corresponding delta I. Okay, so what I'm basically getting is X minus delta 1 to X plus delta 1 should be a subset in A1. X minus delta 2 to X plus delta 2 should be a subset in A2, and so on, till X minus delta n to X plus delta n should be a subset in AN. Let delta be equal to minima of all these delta I values. Okay. For all I equals to 1 select n, all the delta i's have a minima value delta I delta. Okay. Now this delta is definitely positive because I have a finite number of deltas. It could be 1, it could be 10, it could be 100, it could be 1000. It could be 1000 to the power 1000. But as long as the number of sets is finite, the minima of these things is going to be one of the delta values itself. And so the minimum is going to be a positive number. So this delta is a positive number. And this delta is less than or equal to each delta I. So what this implies is that X minus delta to X plus delta is going to be a set which is shrinker, which is narrower than delta 1 to delta 1. Right? In the limiting case, it's going to be equal. So this is my point X. This is my X plus delta 1. And this is my X plus delta. Because delta is smaller than all the delta values. If delta 1 were the smallest, then in that case, it's going to be here. But in no case is it going to be further away from this delta 1. And that is going to be true for each of these things. So that's what I can write, that x minus delta to x plus delta is also a subset of this thing, and so on. Okay. So graphically, if I show what I've done is, I've shown that there is some number x, and around these number x, there are different delta values. This is delta 1, this is delta 2, this is, let's say, delta 3, and so on. So I take the minimum of these delta values and say that focus on the smallest of these delta values. And the smallest delta values will be contained in each of these sets. So this x minus delta to x plus delta is contained in each of these sets, which implies that x minus delta to x plus delta is contained in intersection of AI for I equals to 1 से लेके. So I started with x belonging to intersection AI, and I end up at x minus delta to x plus delta in intersection AI, such that this delta is positive. So this completes the proof that an arbitrary union of open sets is open. Now I'm spending too much time on this proof. The proof is not important, but the result is very, very important. It is so important that DSE asks it every alternate year. You can go through the past years, you'll find this thing in one way or the another. In every alternate year, they are going to ask something of this format. Okay, so it is absolutely crucial knowing this thing. Now let's look at the part where you have an infinite intersection. So let's say that x belongs to I equals to 1 say infinity AI. So the thing that could go wrong here is that when you take a minimum of infinite numbers, a minimum of infinite positive numbers can be 0. So this delta greater than 0, this thing this thing may not be true. I'll make you appreciate this fact with the help of an example. Okay, so let's look at an example where we have an infinite collection of open sets, and their intersection is not their finite intersection is an open set, but their infinite intersection is not an open set. Yeah. So as an example, consider a collection of sets AI such that AI equals to minus 1 by I to 1 by I for all I greater than I belonging to natural numbers, right? Okay, so basically your set A1 is minus 1 to 1, A2 is minus half to half, A3 is minus 1 by 3 to 1 by 3, and so on. Okay. All right. So if I draw these sets on a graph, this is my 0. So this is my set A1. Then this is my set A2. Then this is my set A3. Then I have my set A4. And so on it goes. It keeps on collapsing towards the origin. They are collapsing towards the origin. So, so if I take intersection AI from I equals to 1 se leke n. So you see, every subsequent set is a subset of the previous set. Okay, so as you keep on increasing I, the sets keep on getting smaller and smaller in their length. Okay, so Kanishka, if I take a finite intersection from 1 to n, what is the final set going to be? The intersection of these n sets for some n could be like say 10, 100, whatever.
So minus 1 by n to 1 by n.
Very good. And brackets?
Closed brackets.
Mm,
Open brackets. Sorry,
open
open
brackets.
brackets.
Okay, so this set, Kritika, is this set open or closed? Open or not? I'm not defining closed set. So is this set open or not?
Open.
Yeah, it is open. Okay, so this one is open. So you have an open set right now, minus 1 by n to 1 by n. But if I take an infinite intersection, this is where the question becomes interesting. That what happens with an infinite intersection? So can anybody tell me what's going to be the infinite intersection of these sets? It's an open question.
So a singleton set containing 0.
Very good. Very good. So it's the singleton set containing the element 0. Okay. Now the question is to Kashish. Is the singleton set 0 open or not?
Closed.
Okay, it's not closed because I have not defined closed right now, but yes, it is closed. Okay. So right now I'm only asking open or not, so it's not open. So you're correct. So this is not open. Why is it not open? Because if I construct a real line and I put the number 0 on it, okay, just the number 0. So the idea is that you should be able to construct a neighborhood which is contained inside the set. No matter what neighborhood you construct on both sides, the neighborhood is going to go outside the set. All right, so this is not open. So the infinite intersection of these sets is a singleton point 0, and this singleton point 0 is not an open set. I hope everybody gets this example. Remember this example because you might not be able to remember the statement of the thing that I have told you. Now, this is again one of those things, just this proposition, which I want you to write in your formula sheet, which I ask you to maintain. So write down this proposition in that formula sheet. It's very, very important. Okay. So there are some examples. We already studied this example. Okay. All right. Neighborhood. So I've been using this term neighborhood. So let us define the notion of neighborhood. So the kind of neighborhoods I've been talking about is x minus delta to x plus delta. So this is something called a symmetric neighborhood. It's a symmetric neighborhood because the midpoint of this neighborhood is the element in question itself, that is the point x. But consider a neighborhood x minus 1 to x plus 2. This is also a neighborhood of x. Okay, so imagine a map. Okay, so this is let's say your home. So if you construct a circle with a protractor with one of the point at your house, this is a neighborhood. But at the same time, this is also a neighborhood. Okay, this is also a neighborhood. So it need not be that all neighborhoods of your house that you can construct will have your house as the center. Imagine societies. Your house could be close to the boundary of the society. Okay, you cannot be on the boundary. Like you'll have to live on the wall. I'm saying that let's say the society has a finite thickness wall on which nobody can live. So then everybody who has a house in this society can consider the entire society or any part of it as a neighborhood. Okay, as long as you are in that part. Okay, so for this guy, this is a neighborhood, but this is blue circle is not a neighborhood for the green guy because he's not contained in it. So the idea is that anything that you're not on the boundary of, and you are contained within is your neighborhood. Okay, so that's the definition. The technical definition is that a set U is a neighborhood of a point X if U is a subset of X minus delta to X plus delta for some delta. Okay, so you can construct an X minus delta to X plus delta if you can construct a symmetric neighborhood which is contained inside the original open set U. Original set U, then the U can be considered as any neighborhood. Okay, so if you take this example of a set from, let's say, a point 0, and this is also a neighborhood. It looks very asymmetric, but you can construct a minus delta plus delta thing contained inside this red thing. So yeah, this red thing is a neighborhood of the point 0. Okay. All right. In the next example, okay, a neighborhood of X needn't be an open interval about X. It just has to contain an open interval around X. Okay, so it need not be open. Okay, a neighborhood could be a closed set also, or it could be like this also. It need not be an open set. A neighborhood is anything that contains an open set which contains the element. So one example is for X between A and B, the closed interval A to B is a neighborhood of X since it contains the interval X minus delta to X plus delta. Okay. But closed interval A to B is not a neighborhood of endpoints A and B. So if you construct a closed interval A to B, let's say A is 0 and B is 2. So this set closed 0 to 2 is a neighborhood for all. So 0 to 2 is a neighborhood for all X belonging to 0 to 2. For all X in 0 to 2, it's a neighborhood. For any other thing, it's not. It's not a neighborhood, for X equals to 2. Because if you consider X equals to 2, then it does not contain any X minus delta to X plus delta inside this. Okay, so it's not a neighborhood for X equals to 2. Okay. So now what we are going to do is we are going to define some notions that we defined earlier in terms of neighborhoods instead of X minus delta to X plus delta. Okay, so if you remember the limits definition that we did, the definition of limits was that a sequence xn tends to limit limit n tending to infinity xn is equals to L if for all epsilon greater than 0, there exists delta greater than 0 such that there exists n greater than 0. For every delta greater than 0, there exists n greater than 0 such that mod of L minus delta is less than mod of L minus xn is less than delta for all n greater than capital N. Okay, I should have written this first. Yeah, so this is the definition of limit. So we used to say that you give me any margin of error around L. This was your margin of error. So what we used to do is we used to have this L thing and we used to say that give me a margin of error around L. And this was your sequence. We used to say that after some element N, all the points of this sequence are going to lie inside the margin of error. That was the definition, that mod L minus xn will be less than the margin of error for all elements coming after this capital N. Now this margin of error, when it was defined, this was defined symmetrically about L. If you notice this thing, it was given a thing plus delta minus delta around L, which was symmetric around L. So what we are saying right now is that you can make this margin of error asymmetric also. You can say that this margin of error looks like this. So it could very well look like L plus 2 delta and L minus delta. It need not be a symmetric thing. Okay, so even in that case, the condition holds. So we are removing the necessity for symmetry. So we are basically making our definitions broader now. Although there's not much to do here, I'm just giving these definitions because it tells us an important thing, that these definitions are not really dependent on symmetry of delta. Okay, the delta need not be symmetric. The delta needs to be positive on both the directions, but it need not really be symmetric. That's all I want you to take away from here. So whatever we had in terms of minus epsilon minus plus epsilon, we can make it minus epsilon 1 plus epsilon 2 and so on. Okay, so that's all there is to this part. So it doesn't add much to what we already know. So I'm not going to get into the proof of this thing, but it's there if you want to read it. Let's move to closed sets. Okay, the most important things is sets are not doors. Okay, sets are not doors. Doors are either closed or open. If a door is not closed, it's open. If a door is not open, it's closed. Okay, but sets are not like that. If a set is not open, it does not imply that it is closed. Okay, so in the set of all sets, if this is the set of open sets, this is the set of closed sets, we'll actually see that there's going to be an intersection also. This is the set of closed sets. And this is a whole lot of sets which are neither open nor closed. So let's define closed sets first, then we'll look at what is this intersection, and then we'll look at what are these things outside these two sets. So the definition of a closed set is that a set is closed if its complement is open. Okay, so we know the complement. All right, so we were talking about a closed set. I think, yeah, Himandi gave us a closed set earlier, which was closed 2 to 4, I think. So Yuvakshi, let's start with this set 2 to 4. Tell me the complement of this set. Let me say that the set A is 2 to 4. So what is going to be the complement of this set?
So minus infinity to 2 and 4 to infinity union.
Sets like brackets?
Sir, open at minus infinity and open at 2 and open at 4 and open at infinity positive.
Good job. Okay, so yeah, so this is my A complement, right? So A complement is, this part is open. This part is open. I'm not saying it is open because it looks like this. It is open because you can, for any point, you can construct an interval around it. I'm not saying that just because this looks like this circular brackets, it's open. I'm saying check it with the definition that we are given now. Okay, so if you construct this interval and this interval, here you take any element, here you can construct an interval around it. So all these elements will have intervals around it in the set. So this part is open, and same applies here. So this part is open. So you have a union of two open sets which has to be open. So A complement is open, and that's why this thing is closed. But at the same time, we consider another set B, which is, let's say, closed 2 to open 4. Then this thing is neither open nor closed. Right? Because this thing is definitely not open. If I look at B complement now, if I look at B complement, So it will be negative infinity to 2 open, union closed 4 to infinity. So if you have closed 4 here, then this 0.4 cannot be contained in any interval inside the set. You take any interval, the left side will protrude outside the set. Okay, so this thing is definitely not open. And this thing is also not open. So the set B is neither open nor closed. Okay. So the set of rational numbers. Okay, no, wait. I have to do this first. Yeah, the empty set phi and R are both open and closed. So I said that there's going to be an intersection of these two sets here in the Venn diagram. Is the Venn diagram. So the other slide, I think. Yeah. So there's going to be an intersection here. So the intersection is the set, null set, and R. So these are both open and closed. So these are both open and closed. Checking that R is open is very easy. Checking that R is open is very easy. So R is open because if you take any element in R, you can construct an interval around it. So this thing is pretty straightforward, which basically gives that R complement, which is the null set. This is closed. The second part is R is closed, which implies that phi is open. So this thing we will still see in some time. We'll look at this thing in some time. Okay, why this is true after we look at the definition of the formal definition of closed sets. This is just a definition which says that if your complement is open, then you're closed. We'll look at one more definition of closed sets, in which case it will become amply clear how R is a closed set. Yeah. Okay. The set of rational numbers Q is neither open nor closed. Okay, so again an important example. So if you look at rational numbers, why is it neither open nor closed? It isn't open because every neighborhood of a rational number contains irrational numbers. So if you just look at the set of rational numbers, okay, so the rational numbers are going to look like this. Okay. Now there's some properties here. So if Q1 comma Q2 are rational numbers, then there exists infinite rationals between them, and there exist infinite irrationals between them. Okay, so you take any two rational numbers, Q1 and Q2. You will have infinite rationals and infinite irrationals between them. Q1 not equals to Q, okay? Q1 not equals to Q2. That's crucial. You cannot take the same point. Then it's not going to be true. But even if they are a millimeter apart, that is 10 to the power minus 3 apart, even in that case, you'll have infinite rationals and irrationals between them. So this is the property of, this is called property of density. Property of density. Density of rational and irrational numbers. Okay. The same thing holds other way around also, by the way. The second corollary of this thing is that if R1 and R2 are irrationals, I call irrational as QC, then there exists infinite rationals between them. Again, R1 not equals to R2, and there exists infinite irrationals between them. Okay, so these four concepts related, but very easy to remember. So this is going to help us prove that the set of rational numbers is neither open nor closed. So let us take the real number line and take any two rational numbers on it, Q1 and Q2. Oh, sorry. Let's take any rational number Q1 on it. Okay. So the set Q, which is a subset of R, this is going to be open if there exists Q1 minus delta to Q1 plus delta subset of Q for all Q1. So you should be able to generate some delta value positive such that this set will have only rationals in it. Now, your delta could be rational or it could be irrational. Okay, if it is rational, then you just look at these 2 points, Q1 and Q1 plus delta. Between these two rationals, there's going to be infinite irrationals. So there's going to be a lot of irrational numbers here. So for delta being rationals, you can show that Q is not open. And for delta irrational, if delta were irrational, then Q1 plus delta and Q1 minus delta, they both become irrational. Okay, because you see 2 plus root 3 and 2 minus root 3, they are both irrational numbers. Okay, so even if Q1 was rational, Q1 plus delta and Q1 minus delta become irrationals. So between these two irrational numbers, you get infinite irrationals. So again, you get the result that Q is not open. So by this logic, Q is not open. And when you do the same exercise on the set of irrational numbers Q complement, you see that Q complement is also not open, which implies that Q is not closed. Again, the proofs are not at all important. When you look at the past years, I've given them at the end of the chapter, like I always do. Okay, I've given the past years at the end of the chapter. So when you look at them, you realize the proofs are not at all important. You just need to remember the results. So maybe you can print out this particular document and highlight them and keep them, because these are low hanging fruits. What are low hanging fruits? Easy things, easy pickings in an exam. You look at a question, if you know this theory, you can do it in 30 seconds and move on. You get 3 marks in 30 seconds, which is great, right? So this topic is very, very nice. Short, they ask one question or maybe 2 questions sometimes. Okay, where was I? Okay, so this is another proposition. A set F is closed if and only if every limit of convergent sequence in F belongs to F. So this is a definition of closed sets. This says that a set is closed if any sequence in that set is going to have its limit inside the set. Okay, so that's the statement. Okay, so the statement is a set is closed if the limit of any convergent sequence inside the set is also inside the set. So for any sequence inside the set, the limit is also inside the set. So let's show this with an example how this is untrue for an open set. Let's say I take the set 0 to 2 and consider the sequence 1 by n. So the sequence 1 by n is basically 1, 1 by 2, 1 by 3, 1 by 4, and so on. The limit of this thing is, yeah, Anuradha, what is the limit of 1 by n sequence?
0.
Very good. Okay. So you start from here, 1, half, 1 by 3, 1 by 4, 1 by 5, 6, 7, 8, 9. All these points, they belong to the set 0 to 1 open. But the final point 0, it does not belong to the set 0 to 1 open. So the entire sequence lies inside the set, but its limit does not lie inside the set. You'll never find such a situation for a closed set. For a closed set, if the entire sequence lies inside the set, then its limit also lies inside the set. If the sequence lies partially inside the set, then it's not applicable. It's applicable only when the entire sequence lies inside the set. Okay. So what we have now is, what do we have now? Yeah, we have a definition which we are going to apply on R. R is closed. I have already checked that R is open. Now I want to check R is closed. So let's use this definition. The definition says that any convergent sequence inside the set should have its limit inside the set. Okay. So on the real number line, you take any sequence. Obviously, its limit is going to be a real line on the real line, right? Where will it go? You cannot have a real sequence just limit becomes complex numbers, right? It's not like you are going 1 minus 1, 1 minus 1, suddenly iota. It doesn't happen like that, right? So we take any sequence, any convergent sequence. कहाँ जाएगा? घूम फिर के real number line में आएगा. So if you take the entire set R, it is definitely closed, which implies that its complement phi is open. Okay, so phi is also both closed and open. So the first statement was R open, which gave me phi closed, and now I have R closed, which gives me phi open. So both these sets are both open and closed. And in fact, they are going to be the only two sets on the real line which obey this property. There's going to be nothing else other than this. Okay, so these are going to be the only sets on the real line which are going to obey this particular property. Okay. Again, skipping the proof because not important. Proofs are not important. Remembering and visualizing the results is important. Okay, so that's why I try to draw as many graphs as I can so that you can remember it pictorially. And remembering pictorially is easier than just me blabbering about epsilons and deltas. I mean, I'll just scare you. You'll think it's new coronavirus variant, maybe. What is this? So it's important to visualize things, and maybe you can remember it better. That would be my hope. But I'll always recommend to revise the chapter once more because this is a new topic. None of you might have read it. So just revise, go over the chapter once. I'll share it on YouTube. Watch it at 2x speed. I don't care, but just revise it once. So then there are a few examples. I've already talked about these examples. 0 to 1 is closed. Okay. This next proposition, very important. An arbitrary intersection of closed sets is closed and a finite union of closed sets is closed. Okay, so let's compare these two propositions. The first proposition was, where is that? First proposition. Yeah. Okay. So this was the first proposition that we had. And now we have this proposition. Where is it? This was proposition 1. This is proposition 2. So what's happening is union becomes intersection, open becomes closed. Okay. And intersection becomes union, open becomes closed. So in the first proposition, we had union AI from I equals to 1, say infinity or n was open, but union of AI for I equals to 1, say n was also open, sorry, intersection. Okay. But if I took an infinite intersection, what would this be? This is just proposition 1, nothing else right now. I've not started comparing them. Proposition 1, infinite intersection of open sets. What
So
could it be?
closed.
Okay, so Kanishka gives me.
Singleton set.
Okay, so Kanishka is giving me an answer closed sets. I don't want any more details. I just want open, close, or neither. So these are your three options: open, closed, open, and neither. So I have one vote for closed. I want everybody to tell me. Please give me one of these options. Yeah, so you can type it in the chat box. You don't have to start your mic. You can say A, B, or C. But I want all students present to give me an answer. I don't care if you copy somebody's answer or you say anything. So Kashish is for closed. Anuradha is for closed. Kanishka is for closed. What about others?
Closed.
Okay, who was this? I'm sorry.
Kritika.
Hi, Kritika. So Kritika also votes for closed. Let me add another answer. Can't say. Does that change your opinion? Think about such. Make an example in your head. Why don't you make an example? This is all about imagination. Okay, topology, like I told you, there's not going to be any solving here. So in your head, imagine open sets and think of certain examples. Okay, I gave you definitely one example in which intersection was giving a singleton set. But what if there is an example where it is giving some other output? And why aren't others speaking up? Himandi and Yuvakshi, take your time, but give me an answer. Or just tell me that you're not getting it. I like it if you guys are interactive. Nobody wants to change their answer? Okay, so the actual answer is can't say. You cannot say because take this example. AI is 0 to 1 for all I. Okay, so Kanishka, what is going to be intersection AI for I equals to 1 silica infinity? If every set is open 0 to 1, what is going to be the intersection of all these sets?
So the midpoint 0.5.
Okay, I'm saying A1 is open 0 to 1. I'm saying A2 is also open 0 to 1. What is the intersection of A1 and A2?
0 to 1.
Okay, then I add another set A3 0 to 1. So what is going to be the intersection of these three sets?
The set itself.
So what is
Zero.
going to be the infinite intersection AI?
0 to 1.
Very good. 0 to 1. Right. Earlier you were getting 0 because things were collapsing. Now it's not. Don't try to remember things like that. Okay, so that is a wrong way to learn. Case to case basis. Okay, so in this case, the set is not collapsing. The sets are not collapsing on each other. It's a constant thing. So you take finite or you take infinite intersection. It is going to be open 0 to 1. So in this case, this thing is open. In the earlier case, I drew it as closed. In some other case, you will have an infinite intersection of sets, which is going to be neither. So neither means something of this format. Okay, so your homework. So the correct answer is can't say here. You can have anything. You can have open, you can have close, you can have neither. So your homework is construct. So this is going to be about imagination and how well you can imagine things. Okay, so construct collection sets AI such that infinite intersection AI is neither an open set nor closed. Okay, so think about it. Take some time. Don't be like 2 minutes dekha nahi hua. Don't give up so easily, because the more you think about it, the more this topic will get clearer. And like I tell you, it's a very low hanging fruit for DSE. Almost nobody gets it correct because nobody has done this. Nobody is learning this. And even if they are, they just go by practicing the past years. DSE does not always ask the same question. It asks something related. They try to twist things a little bit. Okay. So anyway, this is open, this is open, this is open or closed or neither. Anything can happen. Now, what about this thing? An arbitrary intersection of closed sets is closed. So if you take a collection of sets BI, which is closed, then infinite or finite intersection. Okay, this is bad. Let me copy this. Okay, so let's look at the second thing. So intersection BI for I equals to 1 select A infinity is going to be closed. Okay, so each BI is closed. And a finite union is going to be closed, whereas no, so finite union, n or infinity. Intersection can be arbitrary. Union for finite, it is closed, but if you have infinite union, then it could be anything, open, closed, or neither. Okay. The proof of this thing is just De Morgan's laws. So let's look at the proof. The proof is pretty interesting. So remember De Morgan's laws. What was De Morgan's law? So just to clarify De Morgan's law, revise De Morgan's laws once more, although we did it in the first 2 chapters, but you might have forgotten. So it says that A union B, a complement, is equals to A complement intersection B complement. And union of some sets Si is equals to a complement is intersection Si complements. Okay. And the reverse also holds, by the way. Intersection SI's whole complement is going to be union of SI complements. let F be an arbitrary collection of closed sets. So if every set F is, so each F is closed, we need to show that intersection Fi is closed. Right. Now, since each F is closed, what it means is that F complement is open, because that's the relationship. So this thing just implies that F complement is open. So each Fi is closed, then every Fi complement is open. So by De Morgan's laws, we just have that intersection Fi is the whole complement. Okay, so I want to show this as closed, right? I have to show that the intersection Fi is closed. So I just show that intersection Fi ka complement is open, then this thing is automatically done, right? Because if intersection Fi is a set, and if this set's complement is open, then this entire set becomes closed. Okay, so when you're looking at intersection Fi, start looking at intersection Fi itself as some set S. So I have to show that this set S is closed. So what I do is S complement open bata do. So how do you do that? You start with S complement. This is union of FICs. Now each of these Fi is closed. So each of these FICs is open. So union of FICs is open. So this entire thing is open. So since this entire thing is open, then since this set ka complement is open, then this set itself must be closed. Right. And a similar proof happens for the union thing. So finite union of closed sets ka complement becomes a finite intersection of open sets. And I know that finite intersection of open sets is open. So this entire complement is open. This entire complement is open. So this set itself becomes closed. Again, proofs not important. Results and your visuals are important. Okay. So let's look at one last visual for today. The set In, which is 1 by n to 1 minus 1 by n for n greater than or equal to 2, let's say. For n equals to 1, this becomes 1 to 0, which is not happening. So I'm going to define it from 2 onwards. So I2 is going to be half to half, which is basically just singleton set half. I3 is going to be 1/3 to 2/3. I4 is going to be 1/4 to 2/4, and so on. Okay. So let's look at this thing. So my set AI is 1 by n to 1 minus 1 by n for n greater than equals to 2. So the sets look like singleton half, 1 by 3 to 2 by 3, 1 by 4 to 3 by 4, 1 by 5 to 4 by 5, and so on. So on the real number line, I'll start with half. This is my set A1. Then set A2 will look like this. Half to half, 1 by 3 to 2 by 3. Next set will look like this. A3, it's going to be 1 by 4 to 3 by 4. And then it keeps on increasing. So both boundaries keep shifting away. So the sets are expanding. So the interesting result is obviously about the unions. So let's look at a finite union and infinite union. So if I just look at a finite union of these 4 sets or 5 sets, is going to be this largest set, which is definitely a closed set. Okay, so finite union being finite is okay, but let's look at the infinite union. So question is, what is infinite union of these AI sets? What is the infinite union of these AI sets? Can anybody tell me what's going to be the infinite union of these sets? Okay, let's proceed in an orderly manner. Let's look at the left boundary. Okay, so what is limit n tending to infinity 1 by n?
0.
0. Very good. Let's look at the right boundary. What is limit n tending to infinity 1 minus 1 by n?
1.
1. Very good. So this union is something of the format 0 to 1. The only thing to decide right now is brackets. Okay, so will it be closed or will it be open? So being closed implies that I am implying that 0 is contained in this union. All right, but it's not. You see, this is my 0 and this is my 1. Now, as you keep reducing n, this boundary keeps on shifting towards left, but it will never reach exact 0. So 0 cannot be reached for these sets. So this infinite union will not ever reach 0. So this is going to be open at 0. Same happens to the right. The right boundary keeps getting closer and closer. It will reach 0.9. It will reach 0.99. It will reach 0.999 and so on. It will reach every point before 1. So every point before 1 is going to be contained in some set here, but 1 is not going to be contained in anything. So this infinite intersection is open set 0 to 1. So you have an example of an infinite union of closed sets, which is giving the final set as open. Okay. All right, so this is important. This is important, and the only way to understand the how to do problems is the best examples are from past years. It's very difficult to build some examples which are not like that, although I'll be sharing a test with you guys on topology after doing past years. I want you to do past years first, test later. Okay. So think about these things. Look at the problems. Maybe try it out with the help of some examples. Okay. So try to build like this question number 33 here. So set 0, 1. So think about some sets which can lead to an intersection being 0, 1. Some sets for which the union, a finite union is 0, 1 and so on. Okay. Okay, so that's going to be it. Okay, yeah, so do the past years and then we'll discuss them. There's not much to do. Like I told you, it's an easy topic, but it's new. So that's why it could be a little challenging at first. So do the problems, we'll discuss them sometime next week. Okay, in the weekdays, we are going to take this up. We're going to take this up and then sequences. I don't think you guys have done the problem set, so I'm going to take doubts again this week, but do them. Sequences is very important. Okay, so let's end this lecture now. I don't want to start a new topic. So let's end this lecture for now, and we'll meet tomorrow evening with microeconomics lecture. All right, I'll see you guys tomorrow then. See the videos again. Ask me any doubts that you have from this chapter. Okay.
So tomorrow in the evening or 11 to 1?
Sorry, what? I couldn't hear you clearly, Kritika.
I'm asking for tomorrow in the evening or 11 to 1 because
Evening. Do
okay.
it in the evening. Okay.